Imagine an object so dense, so heavy, that its own gravity becomes an inescapable trap. Picture a point in space where the familiar rules of our universe are bent and broken, where time itself can grind to a halt, and where not even light, the fastest thing in the cosmos, can escape. This is the world of the black hole, one of the most extreme and enigmatic phenomena in all of nature. According to Albert Einstein's general theory of relativity, when a sufficient amount of matter is compressed into a sufficiently small volume, the force of gravity becomes so overwhelming that it creates a one-way membrane in space-time, a point of no return known as the event horizon. Anything that crosses this boundary is lost to the outside universe forever, pulled inexorably towards a central singularity, a point of infinite density where our current laws of physics break down. The size of this event horizon, the Schwarzschild radius, depends on the mass of the object. For our own sun to become a black hole, it would need to be squeezed down to a diameter of just 3 kilometers. At that point, its density would be astronomical, far beyond anything we encounter in our everyday world. For smaller objects, the powerful quantum forces that operate between subatomic particles, the electromagnetic force and the nuclear forces, are strong enough to resist the inward pull of gravity, preventing them from collapsing into such an extreme state. But for the most massive stars in the universe, a different fate awaits. Black holes are not just a theoretical curiosity. They are a ubiquitous feature of our cosmos, and they come in a vast range of sizes. Stellar mass black holes are the ghosts of dead stars. When a star, more than about 10 times the mass of our sun, exhausts its nuclear fuel, it can no longer support its own weight against the crushing force of gravity. Its core collapses catastrophically, triggering a spectacular supernova explosion that blasts its outer layers into space. What remains behind is a compact remnant, a black hole with a mass a few times that of our sun. Our own Milky Way galaxy is thought to be littered with over 1 billion of these stellar ghosts, most of them dark and invisible, wandering silently through the interstellar void. We can only detect them indirectly when they are locked in a binary system with a normal star, their immense gravity pulling material from their companion into a glowing, superheated accretion disk. At the other end of the scale are the supermassive black holes, the true giants of the cosmos. These behemoths, with masses ranging from millions to billions of times that of our sun, are thought to reside at the heart of nearly every large galaxy, including our own. At the center of the Milky Way lurks Sagittarius A, a supermassive black hole with a mass of about 4 million suns. These galactic monsters are the engines that power the most luminous objects in the universe, quasars. A quasar is an incredibly bright, distant galactic nucleus, where a supermassive black hole is actively feeding on a vast disk of gas and dust, releasing an amount of energy that can outshine its entire host galaxy by a factor of thousands. Between these two extremes lies a more elusive class, intermediate mass black holes. These are thought to form from the collapse of the very first generation of stars, population 3 stars, which were much more massive than the stars we see today, with masses over 100 times that of our sun. These primordial giants would have burned through their fuel very quickly, collapsing directly into intermediate mass black holes and potentially triggering some of the powerful gamma ray bursts we observe in the distant universe. All of these black holes, from the stellar to the supermassive, are considered macroscopic. They are large enough that their behavior is, for the most part, well described by the classical laws of Einstein's general relativity. But there may be another, much stranger, class of black holes, a class for which the bizarre rules of the quantum world become all important. These are the primordial black holes, hypothetical objects that may have formed not from the collapse of stars, but from the extreme, high-density conditions of the very early universe, just a fraction of a second after the Big Bang. These primordial black holes could have a vast range of masses, from the supermassive down to the microscopic. A primordial black hole with a mass less than that of our moon could be smaller than a micron. Yet its gravitational influence could still be significant, and some have speculated that these objects could even constitute the mysterious dark matter that makes up the bulk of the universe's mass. It is at this microscopic scale that our classical understanding of black holes begins to break down, and a new, more profound, and more mysterious picture begins to emerge. In 1974, the physicist Stephen Hawking made a discovery that would forever change our understanding of black holes and would forge a deep and unexpected link between the two great pillars of modern physics, general relativity and quantum mechanics. He showed that black holes are not, in fact, completely black. Due to quantum effects at the very edge of the event horizon, they should slowly emit a faint thermal radiation, now known as Hawking radiation. This discovery was a theoretical tour de force, a beautiful and subtle calculation that showed how the constant roiling sea of virtual particles in the quantum vacuum could be influenced by the intense gravity of a black hole. In the empty space near an event horizon, a virtual particle-antiparticle pair can be created. Normally, this pair would quickly annihilate each other and disappear. But if one particle falls into the black hole while the other escapes, the escaping particle can become a real particle, carrying away a tiny amount of the black hole's mass energy. The black hole, in effect, radiates. The temperature of this radiation is inversely proportional to the black hole's mass. The smaller the black hole, the hotter it is, and the more rapidly it radiates. For a large, stellar mass black hole, this temperature is incredibly low, far colder than the cosmic microwave background, making the radiation practically undetectable. But for a small, primordial black hole, the temperature could be incredibly high. A black hole with the mass of a large mountain would have a temperature of about 10 to the power of 12 Kelvin, and it would radiate away its mass not just as photons, but as a shower of electrons, positrons, and other energetic particles. This process of radiation means that black holes are not eternal. They evaporate. As a black hole radiates, it loses mass, which, due to the inverse relationship, causes it to get hotter and radiate even faster. This creates a runaway process, an accelerating evaporation that culminates in a final, explosive burst of energy. The lifetime of a black hole depends dramatically on its initial mass. A solar mass black hole would take an almost unimaginable 10 to the power of 64 years to evaporate, far longer than the current age of the universe. But a primordial black hole with a mass of about 10 to the power of 12 kilograms would have a lifetime of roughly 10 billion years, about the age of our universe. This means that such black holes, if they were formed in the Big Bang, should be exploding right now, releasing their final energetic death cry in a flash of gamma rays. The search for these telltale flashes is an active, if so far unsuccessful, area of observational astronomy. The black holes that are small enough to be significantly affected by these quantum processes, those with masses below about 10 to the power of 12 kilograms, are what we call quantum black holes. Their behavior is no longer governed solely by classical gravity, but by a complex interplay between general relativity, quantum field theory, and thermodynamics. Hawking's discovery was a monumental first step towards a unified theory of quantum gravity, a theory that could describe the universe at its most extreme and fundamental level. But it was only a first step. His analysis was semi-classical, meaning it treated the radiating particles quantum mechanically, but treated the space-time of the black hole classically. A full understanding of the formation and evaporation of the smallest possible black holes. Those with a mass and size approaching the Planck scale, the fundamental limit where the effects of quantum gravity become dominant, will require a true, and as yet undiscovered, theory of everything. Such a theory might reveal even stranger possibilities, such as the idea that an evaporating black hole does not disappear completely, but leaves behind a tiny, stable, Planck mass relic, a quantum fossil that could hold the secrets of the information that fell into the black hole. The quest for a theory of quantum gravity, the holy grail of modern theoretical physics, has led scientists down a number of strange and beautiful paths. And one of the most intriguing of these is the idea of extra hidden dimensions of space. This is a concept that dates back to the 1920s, when the physicists Theodore Kaluza and Oscar Klein proposed that our universe might have a fifth dimension, a dimension that is curled up or compactified into a tiny circle at every point in our familiar three-dimensional space. They showed that if this were the case, then Einstein's theory of gravity in 5 dimensions would look, in our 4-dimensional world, like a combination of gravity and electromagnetism. It was a beautiful and elegant idea, a first, tantalizing hint that the different forces of nature could be unified through the geometry of higher dimensions. The idea of extra dimensions was later revived and expanded in the context of string theory. In its modern form, known as M-theory, the theory requires the existence of a total of 11 space-time dimensions, 10 of space and 1 of time. The extra 7 spatial dimensions are thought to be curled up into a complex, 6-dimensional geometrical shape known as a Calabi-Yau manifold. The precise shape and size of this manifold determines the vibrational patterns of the fundamental strings, and therefore, the properties of all the particles and forces in our universe. In the standard picture, these extra dimensions are thought to be incredibly small, on the order of the Planck length. This would mean that they have no noticeable effect on the behavior of macroscopic black holes. But in some, more recent, brain world models, it is possible that some of these extra dimensions are much larger. In these models, the particles and forces of the standard model are confined to our 3-dimensional brain, while gravity is free to propagate in the higher dimensional bulk. This could have a dramatic effect on the strength of gravity at short distances. The familiar inverse square law of gravity would break down, and gravity would become much, much stronger at scales comparable to the size of the extra dimensions. This has a profound implication, the true of fundamental scale of quantum gravity. The Planck scale could be much lower than the traditional value of 10 to the power of 19 electron volts. It could, in fact, be as low as a few tera-electron volts, a range of energy that is just now being probed by our most powerful particle accelerator, the Large Hadron Collider. This raises the astonishing and exciting possibility that we could create microscopic quantum black holes in the laboratory. The LHC works by accelerating protons to nearly the speed of light and then smashing them together. Each proton carries an energy of around 7 tera-electron volts. In a head-on collision, the total energy is 14 tera-electron volts, all concentrated in a tiny subatomic volume. In the standard picture of gravity, this is far, far too low an energy to create a black hole. The proton's mass is about 10 to the power of 19 times smaller than the Planck mass, and the density achieved in a collision is many orders of magnitude below the Planck density required for gravitational collapse. To create a black hole in a collision, we would need to accelerate a proton to the Planck energy, an energy that is a quadrillion times higher than what the LHC can achieve. Building such an accelerator would require a machine the size of our galaxy. But if the idea of large extra dimensions is correct, and the true Planck scale is in the tera-electron volt range, then the story changes completely. The high-energy collisions at the LHC could, in principle, have enough energy to briefly compress a sufficient amount of mass energy into a small enough volume to create a tiny microscopic black hole. These would not be the dangerous galaxy-eating monsters of science fiction. They would be subatomic in size, and they would evaporate almost instantaneously in about 10 to the power of minus 27 seconds via Hawking radiation. They would decay into a spectacular spherical burst of high-energy particles, photons, electrons, quarks, gluons that would light up our detectors like a microscopic firework. A unique and unmistakable signature of new exotic physics. The search for such events has been one of the major goals of the LHC experimental program. So far, no evidence for the production of microscopic black holes has been found. This has placed strong constraints on many of the models with large extra dimensions, pushing the possible scale of quantum gravity to higher and higher energies. But the search continues. The discovery of microscopic black holes at the LHC would be a scientific revolution of the highest order. It would be the first direct experimental evidence for the existence of extra dimensions of space. It would provide us with a laboratory to study the physics of quantum gravity, to test the predictions of Hawking radiation, and to probe the very fabric of space-time at its most fundamental level. It would be a window into a new, hidden reality. A reality that has, until now, been completely inaccessible to us. The discovery of Hawking radiation and the subsequent paradox of information loss has been one of the most powerful drivers of theoretical progress in physics for the past 50 years. It is a problem that lies right at the intersection of our two most fundamental theories, general relativity and quantum mechanics, and its resolution is thought to be a crucial key to unlocking the secrets of quantum gravity. At its heart, the paradox is a clash of two, seemingly inviolable principles. General relativity, with its description of a smooth space-time and an absolute event horizon, seems to imply that any information that falls into a black hole is lost to the outside universe forever, causally disconnected and irretrievable. Quantum mechanics, on the other hand, insists on the principle of unitarity, the idea that information is never truly destroyed. The total amount of information in a closed system must be conserved. A process may be scrambled, its information hidden in complex correlations, but it can, in principle, always be unscrambled. So, what happens when a black hole, which has swallowed a vast amount of information, completely evaporates into a seemingly random thermal bath of Hawking radiation? Is the information lost, in violation of quantum mechanics, or does it somehow get out, in violation of general relativity's principle of locality and causality? This is the information paradox for many years. Stephen Hawking himself was a firm believer in information loss. He argued that the process of black hole evaporation was fundamentally non-unitary, and that we would have to modify the laws of quantum mechanics to accommodate it. But most of the theoretical physics community, particularly those working in string theory, resisted this conclusion. The principle of unitarity is so central to the structure of quantum mechanics that to abandon it would be to abandon the very foundations of our most successful physical theory. This led to a decades-long search for a mechanism by which the information could escape. One of the most powerful and influential ideas to emerge from this search is the holographic principle, first proposed by Gerard 't Hooft and later developed by Leonard Susskind. The principle was motivated by the discovery that the entropy of a black hole, its information content, is proportional not to its volume, as one might expect, but to the area of its event horizon. This is a strange and profound result. It suggests that all the information about the three-dimensional interior of a black hole can be somehow encoded on its two-dimensional surface. This is like a hologram, where a two-dimensional film can encode all the information needed to create a three-dimensional image. The holographic principle generalizes this idea to the entire universe. It suggests that the reality we perceive as a three-dimensional space with gravity might be a holographic projection of a more fundamental two-dimensional quantum field theory that lives on the boundary of our space-time, a theory that does not include gravity. This is the essence of the ADS-CFT correspondence, a specific and powerful mathematical realization of the holographic principle discovered by Juan Maldacena, which shows an exact equivalence between a theory of gravity in a five-dimensional anti-de Sitter space and a four-dimensional quantum field theory living on its boundary. This correspondence provides a powerful tool for studying quantum gravity, as it allows us to translate difficult problems in gravity into more tractable problems in a non-gravitational quantum field theory, a theory that is, by definition, unitary. In the context of the information paradox, the holographic principle suggests that the information is never truly inside the black hole in the classical sense. It is stored on the event horizon, and as the black hole evaporates, this information is slowly and subtly encoded in the quantum correlations of the outgoing Hawking radiation. The process is unitary, and no information is lost. Another, more recent, and even more startling idea is the ER-EPR conjecture, proposed by Leonard Susskind and Juan Maldacena. This conjecture proposes a deep and unexpected connection between two of Einstein's most famous ideas, the spooky action at a distance of quantum entanglement and the concept of a wormhole or Einstein-Rosen bridge. The conjecture states that two entangled particles are, in a sense, connected by a microscopic, non-traversable wormhole. The strange, non-local correlation of entanglement is a manifestation of this deep, geometrical connection in space-time. In the context of a black hole, this idea has profound implications. The outgoing Hawking radiation is entangled with the particles that fell into the black hole. The ERR-EPR conjecture would suggest that the inside of the black hole is geometrically connected to the outgoing radiation via a vast network of microscopic wormholes. The information is not trapped inside. It is non-locally connected to the outside. These are highly abstract and mathematical ideas, and they are still the subject of intense research and debate. But they are a testament to the incredible creativity and power of theoretical physics. They show how a deep conceptual paradox, born from the clash of our two greatest theories, can become a powerful engine for discovery, leading us to new and profound insights into the nature of space-time, of information, and of reality itself. The black hole information paradox is not just a technical puzzle. It is a koan, a riddle that is forcing us to abandon our classical intuitions and to embrace a new, more holistic and more deeply quantum vision of the cosmos. The formation of black holes is a story of gravitational triumph, a cosmic drama where the relentless inward pull of gravity overcomes all other forces of nature. The most common pathway to a black hole is through the death of a massive star. A star, for most of its life, is a battlefield, a delicate balance between two opposing forces. Gravity, the force that pulls all of its matter inwards, is constantly trying to crush the star. This is counteracted by the outward pressure generated by the intense heat and radiation from the nuclear fusion reactions in its core. As long as the star has fuel to burn, this hydrostatic equilibrium is maintained. But when a massive star, one with a mass more than about 25 times that of our Sun, exhausts its nuclear fuel, the story changes. The fusion reactions in its core cease, the outward pressure vanishes, and gravity wins. The core of the star collapses catastrophically under its own immense weight. This collapse is an incredibly rapid and violent event. In a fraction of a second, a region of matter the size of the Earth is crushed down to a size smaller than a city, reaching densities that are almost beyond comprehension. The outer layers of the star, no longer supported by the core, come crashing down, bounce off the super-dense, newly formed protoneutron star, and are blasted out into space in a spectacular supernova explosion, one of the most energetic events in the universe. But for the most massive stars, even the immense pressure of the neutrons, the neutron degeneracy pressure that supports a neutron star, is not enough to halt the collapse. The gravitational pull is so overwhelming that the core continues to collapse indefinitely, down to a point of infinite density, a singularity. An event horizon forms around this singularity, and a new stellar mass black hole is born. This is the standard picture, but recent observations and theoretical work have revealed a more complex and nuanced story. For stars in a certain mass range, roughly between 8 and 25 solar masses, the collapse of the core can be temporarily halted, forming a neutron star. But the fallback of material from the supernova explosion can then push the mass of the neutron star over its critical limit, causing it to subsequently collapse into a black hole. For even larger stars, those with masses above about 40 times that of the Sun, the collapse can be so rapid and so powerful that it does not even produce a traditional supernova. The star collapses directly into a black hole, swallowing its own explosion in a phenomenon known as a collapser. These events are thought to be the engines behind some of the most powerful explosions in the universe, the long-duration gamma-ray bursts. The formation of supermassive black holes, the behemoths that reside at the centers of galaxies, is a more complex and still not fully understood story. They are too massive to have formed from the collapse of a single star. Instead, they are thought to have grown over cosmic time through a combination of processes. They may have started as seed black holes in the early universe, either from the collapse of the very first massive population 3 stars, or from the direct collapse of vast clouds of primordial gas. These seed black holes would have then grown over billions of years by accreting gas and dust from their host galaxies, and by merging with other black holes during galactic collisions. The James Webb Space Telescope is providing crucial new insights into this process by observing some of the most distant quasars, which are powered by supermassive black holes that had already grown to billions of solar masses when the universe was less than 1 billion years old. The existence of these massive black holes so early in cosmic history is a major challenge to our models of their formation and growth, suggesting that the process may have been much more rapid and efficient than we previously thought. The formation of a black hole is not just an astrophysical event, it is a transformation of the very fabric of reality. A place where matter is crushed out of existence and the laws of physics are pushed to their absolute limits. It is a one-way journey into a realm of mystery, a place from which no information can return. Or so we thought. The no-hair theorem is a profound and elegant statement about the nature of black holes in the context of classical general relativity. It is a concept that strips black holes of all their complexity and reduces them to objects of almost perfect simplicity. The theorem, which was developed through the work of physicists like Werner Israel, Brandon Carter, and Stephen Hawking, states that a stable, stationary black hole, regardless of the intricate details of the matter that collapsed to form it, can be completely and uniquely described by just 3, and only 3, externally observable properties: its total mass, its total electric charge, and its total angular momentum, or spin. All other information about the matter that fell in its chemical composition, its temperature, its shape, its texture is seemingly lost forever behind the event horizon. The black hole, in this sense, has no hair. It has no other distinguishing features, no complex individual characteristics. All black holes with the same mass, charge, and spin are identical and indistinguishable from the outside. This is a remarkable statement. It means that if you were to make a black hole by collapsing a vast cloud of hydrogen gas, and another black hole of the same mass by collapsing a collection of old television sets, the final, stable black holes would be absolutely identical. The immense complexity and information content of the initial matter is wiped clean, leaving behind only the three conserved quantities of mass, charge, and angular momentum. The no-hair theorem is a powerful illustration of the information loss problem. It is the classical statement that a black hole is a perfect information sink. The geometry of space-time around a black hole is determined solely by these three parameters. A non-rotating, uncharged black hole is described by the simple Schwarzschild metric. A rotating black hole is described by the Kerr metric, and a charged, non-rotating black hole is described by the Reissner-Nordstrom metric. The most general case, a rotating, charged black hole, is described by the Kerr-Newman metric. These four solutions to Einstein's field equations are thought to describe all possible, stable, black holes in our universe. This simplicity, however, is a feature of the classical world. When we begin to consider the quantum nature of black holes, the picture becomes more complex. Quantum mechanics suggests that black holes should have a vast number of internal microscopic states, a microscopic hair that is not visible from the outside. The entropy of a black hole, which is proportional to the area of its event horizon, is a measure of this hidden internal information. The challenge for a theory of quantum gravity is to provide a microscopic, statistical explanation for this entropy, to count the number of quantum states that correspond to a given macroscopic black holes. String theory, for example, has had some remarkable successes in this area, being able to precisely calculate the entropy of certain highly symmetric, extremal black holes by counting the number of ways that fundamental strings and branes can be configured to produce the same mass, charge, and spin. This is seen as one of the major triumphs of the theory, a sign that it is on the right track towards a quantum description of gravity. The no-hair theorem, then, may be a classical approximation. From a distance, a black hole may appear simple and featureless, but up close, at the quantum level, it may be a rich and complex object. Its event horizon a shimmering, holographic surface that encodes a vast amount of hidden information. The question of whether this information is ultimately lost or preserved is the question that lies at the heart of the information paradox, and it is a question that will likely not be fully answered until we have a complete and consistent theory of quantum gravity. The theoretical possibility of creating microscopic black holes in high-energy particle collisions, while still unconfirmed, has opened up a fascinating new frontier in experimental physics. It is an idea that connects the largest objects in the universe with the smallest, the force of gravity with the world of particle physics, and it offers a potential, albeit challenging, path to probing the exotic realm of quantum gravity in the laboratory. The production of a black hole in a collision is governed by a simple principle known as the Hoop conjecture, proposed by the physicist Kip Thorne. It states that a black hole will form if, and only if, a sufficient amount of mass energy is compressed into a region of space that is smaller than its own Schwarzschild radius. In the context of a particle collision, this means that the two colliding particles must get closer to each other than the Schwarzschild radius corresponding to their total center of mass energy. In the standard four-dimensional picture of gravity, this is an impossible feat for any conceivable particle accelerator. The Planck energy. The energy at which gravitational effects become strong is about 10 to the power of 16 times higher than the energy of the LHC. But in models with large extra dimensions, as we have seen, the true scale of quantum gravity could be much lower, potentially within the reach of the LHC. If this is the case, then in a tiny fraction of the proton-proton collisions at the LHC, the two colliding partons could get close enough to form a microscopic black hole. The probability, or cross-section. For this process can be estimated using simple geometrical arguments. It is roughly equal to the geometric area of the black hole's event horizon, which is proportional to the square of its Schwarzschild radius. The details of the process are complex, involving the gravitational shock waves of the two ultra-relativistic particles, a phenomenon described by the Eichelberg-Sechsel metric. But the basic idea is that a closed, trapped surface, the mathematical definition of an event horizon, can form in the collision, signaling the birth of a black hole. These microscopic black holes would be incredibly unstable, evaporating almost instantaneously through Hawking radiation. The specific way they decay, however, would be a powerful probe of new physics. In the standard model, a black hole should radiate democratically, emitting all types of particles with a probability that depends only on their mass and spin. But in models with extra dimensions, the black hole could preferentially radiate particles into the higher dimensional bulk, such as gravitons. This would result in a missing energy signature in our detectors, a telltale sign of the existence of extra dimensions. The Hawking radiation from these black holes would also be thermal, with a temperature that depends on the black hole's mass. By measuring the spectrum of the decay products, we could, in principle, measure the temperature of the black hole and test the predictions of Hawking's theory. Furthermore, the final stages of the black hole's evaporation, when it reaches the Planck scale, are a realm where a full theory of quantum gravity is needed. The specific particles and energies emitted in this final burst could provide crucial clues about the nature of this ultimate theory. Are they stable? Planck mass remnants is information preserved. The decay of a microscopic black hole would be a window into the most fundamental secrets of nature. The search for these exotic events at the LHC has, so far, come up empty. No signs of black hole production have been observed. This has placed stringent limits on the models with large extra dimensions, pushing the possible scale of quantum gravity to ever higher energies. It seems that if extra dimensions exist, they are smaller, or their geometry is more complex than the simplest models predicted. But the quest is not over. The LHC is continuing to collect data at higher energies and higher luminosities. And future. More powerful accelerators are being planned. The dream of creating a black hole in the laboratory, of holding a piece of quantum space-time in our hands, is a dream that still inspires and motivates a generation of physicists. It is a long shot, to be sure, but it is a shot worth taking. For the scientific prize would be nothing less than a revolution in our understanding of the universe. In the absence of direct experimental evidence for quantum gravity from particle accelerators, physicists have turned to another, more subtle and more theoretical approach: effective field theory. This is a powerful and pragmatic framework that allows us to study the low-energy consequences of a high-energy theory without knowing all the details of that theory. The basic idea is to integrate out the high-energy physics, to average over the effects of the heavy, unknown particles and the quantum gravitational fluctuations, and to see what subtle, residual effects they leave behind on the low-energy physics that we can observe. In the context of quantum gravity, this means that we can write down and use effective action for our low-energy world, which consists of Einstein's general relativity and the standard model of particle physics, plus an infinite series of small, higher-dimensional correction terms. These correction terms are suppressed by powers of the Planck scale, the fundamental scale of quantum gravity. They represent the faint, low-energy echoes of the unknown, high-energy physics. While these effects are incredibly small, they are, in principle, measurable. And by precisely measuring the properties of particles and forces at low energies, we can place constraints on the possible values of the coefficients of these correction terms, giving us an indirect but powerful Glimpse into the nature of quantum gravity. One of the most important of these correction terms is a potential non-minimal coupling between the Higgs boson and the curvature of space-time. The Higgs boson is a unique and special particle. It is the only fundamental scalar particle in the Standard Model, and its associated field, the Higgs field, is what gives mass to all the other fundamental particles. It is natural to expect that the Higgs field would have a direct coupling to the geometry of space-time, a coupling that is represented by a term in the effective action. This coupling has profound cosmological implications. In the early universe, during the period of cosmic inflation, the Higgs field itself could have played the role of the inflaton, the field that drove the exponential expansion. This is the idea behind Higgs inflation models. The viability of these models depends crucially on the value of this non-minimal coupling constant. By precisely measuring the properties of the cosmic microwave background, which carries the imprint of the inflationary epoch, we can place constraints on these models and, indirectly, on the nature of the interaction between the Higgs field and gravity. Another, related area of research is the effect of these quantum gravitational corrections on the unification of the fundamental forces. In grand unified theories, the strong, weak, and electromagnetic forces are all thought to emerge from a single unified force at very high energies. The success of these theories depends on the precise way that the strengths of the three forces evolve with energy and meet at a single point. The quantum gravitational correction terms can affect this running of the coupling constants, potentially altering the predictions of GUTs and offering a new way to probe the physics at the unification scale. Effective field theory is a subtle and powerful tool. It allows us to make progress in the absence of a complete theory. It is a way of listening for the faint, low-frequency whispers of the high-energy, quantum gravitational world. And while it may not give us the full symphony, it can provide us with crucial notes, with hints and clues that can guide us in our long and difficult quest to construct a final, unified theory of everything. It is a beautiful example of how precision measurements in the world we can access can shed light on the deep and mysterious realities of the world we cannot. The world of quantum gravity is not just a world of microscopic black holes and extra dimensions. It is a world where the very concepts of causality and locality, the bedrock of our classical intuition, may break down. In a classical relativistic world, information cannot travel faster than light, and events can only be influenced by other events in their past light cone. But in a theory of quantum gravity, where space-time itself is subject to quantum fluctuations, this rigid causal structure may become fuzzy or even non-existent at the Planck scale. This has led to the exploration of non-local and acausal theories. Theories where distant points in space-time can be connected in ways that defy our normal understanding. One of the most interesting and well-developed of these is the Leawick model, a type of quantum field theory that introduces new heavy particles with a peculiar property. They have a wrong sign propagator, which effectively means they can travel backwards in time for very short distances. This seemingly bizarre feature has a remarkable consequence. It can cancel out some of the problematic infinite quantities that plague standard quantum field theories, making the theory finite and more mathematically consistent. The price to pay for this mathematical elegance is a tiny, microscopic violation of causality. These violations are confined to the Planck scale and are too small to be observed in any macroscopic experiment. So they do not lead to the familiar paradoxes of time travel, but they do suggest that at the most fundamental level, the strict linear arrow of time may not hold. The universe may have a built-in microscopic acausality that is an essential part of its structure. The study of gravitational scattering at very high energies near the Planck scale has also provided hints of non-local and acausal effects. when we try to calculate the probability of two gravitons scattering off each other at these extreme energies using our standard techniques, we run into problems with unitarity, the principle that probabilities must always add up to 1. However, by using a technique called resummation, where we take into account an infinite series of quantum loop corrections, it is possible to restore unitarity. But this comes at a cost. The resumed graviton propagator, the mathematical object that describes the propagation of a graviton, develops new, complex poles. These poles do not correspond to normal, stable particles. They represent short-lived, unstable resonances, which have been interpreted as the quantum precursors of microscopic black holes. These quantum black holes are not the classical objects of general relativity. They are fuzzy, quantum states that have some of the properties of a black hole, but are not described by a classical singularity or event horizon. And one of their most striking features is that they seem to introduce a degree of non-locality and a causality into the theory. This is perhaps not surprising. A black hole, even a classical one, is a fundamentally non-local object. Its event horizon is a global property of the spacetime. The fact that the quantum precursors of black holes seem to be tied to a microscopic violation of causality is a deep and tantalizing clue. It suggests that the resolution of the conflict between gravity and quantum mechanics may require us to abandon one of our most deeply held intuitions, the idea of a strict, linear, and unbreakable chain of cause and effect. This has led to the development of two related concepts, self-healing and classicalization. Self-healing is the idea that the theory of quantum gravity has a built-in mechanism to prevent the formation of true, problematic singularities. As we approach the Planck scale, the quantum black hole resonances become the dominant effect, effectively healing the spacetime and preventing it from becoming infinitely curved. Classicalization is the idea that as we go to higher and higher energies, the quantum black hole states become more and more numerous and begin to behave more and more like a classical macroscopic black hole. The system, in a sense, classicalizes itself. In this picture, there is a minimal length in nature, on the order of the Planck length, below which it is impossible to probe. Any attempt to do so by using higher and higher energy probes will simply result in the creation of a larger and larger black hole, which actually hides, rather than reveals, the short-distance structure of spacetime. This is a profound and beautiful picture. It suggests that the universe has a built-in, self-regulating mechanism that protects itself from the paradoxes and infinities that have plagued our theories. It suggests that the final theory may be one that is not just mathematically consistent, but is also, in a deep sense, self-healing. The rich and varied zoo of black holes predicted by our theories, the spinning, the charged, the higher dimensional, provides a vast theoretical laboratory for exploring the intricate interplay between gravity, space-time, and the quantum world. The simplest black hole, the non-rotating, uncharged Schwarzschild black hole, is an object of perfect spherical symmetry. But the moment a black hole acquires spin, its character changes dramatically. A Kerr black hole, as it is called, is no longer a simple, static object. Its rotation drags the very fabric of space-time around with it. A phenomenon known as frame dragging. Near the event horizon, this effect is so powerful that it creates a region called the ergosphere, a place where nothing can stand still. Every object, every particle, every beam of light is forced to co-rotate with the black hole. This rotational energy can, in principle, be extracted, a process known as the Penrose process. A particle can enter the ergosphere, split into two, with one piece falling into the black hole and the other escaping with more energy than the original particle had. A spinning black hole can act as a colossal cosmic flywheel, a vast reservoir of rotational energy that can be tapped to power some of the most energetic phenomena in the universe, like the relativistic jets of quasars. The quantum world adds another layer of complexity and wonder. The process of superradiance suggests that a spinning black hole can spontaneously amplify certain quantum fields, creating a black hole bomb that would release its energy in a massive burst. The interaction between the spin of the black hole and the quantum fluctuations of the vacuum is a rich and largely unexplored area of theoretical physics. The addition of electric charge creates a Reissner-Nordstrom black hole, an object with both a gravitational and an electric field. The interplay between these two fundamental forces creates a complex and fascinating structure, with both an outer and an inner event horizon. Classically, it would be possible to travel through the outer horizon and avoid the central singularity, potentially passing through a wormhole into another region of space-time, or even another universe. However, it is thought that these inner horizons are fundamentally unstable, and that any small perturbation would cause them to collapse into a singularity. The quantum effects in a charged black hole are also intriguing. The strong electric field near the event horizon could spontaneously create real electron-positron pairs from the vacuum, a process known as the Schwinger effect, which would act to neutralize the black hole's charge. The study of these more exotic black holes is not just a mathematical exercise. It is a way of probing the deep structure of our physical theories. The existence of solutions with naked singularities not hidden behind an event horizon in some of these models, has led to the formulation of the cosmic censorship conjecture, the idea that nature abhors a naked singularity, and that some, as yet undiscovered, principle of physics must prevent their formation. The world of higher dimensional black holes, predicted by string theory, is even stranger. A black hole in 5 dimensions is not a sphere, but a black ring, and in higher dimensions, a whole zoo of black brains, black strings, and other exotic topologies become possible. The study of these objects is providing deep insights into the mathematical structure of string theory and the nature of quantum gravity. And finally, the development of black hole analogs in the laboratory is allowing us to test some of these exotic ideas experimentally by creating systems in condensed matter physics, like a Bose-Einstein condensate or a flowing fluid, that mimic the properties of a black hole's event horizon. Scientists can study the analog of Hawking radiation and other quantum effects in a controlled laboratory setting. These are not real black holes, but they are governed by similar mathematical equations, and they provide a powerful tool for testing the conceptual framework of black hole thermodynamics and the quantum physics of curved spacetime. The study of black holes, in all their varied and wonderful forms, is one of the most exciting and dynamic frontiers in modern science. They are the ultimate cosmic laboratory, a place where the laws of nature are pushed to their absolute limits and where the deepest secrets of gravity, of space-time, and of the quantum universe are waiting to be revealed. The discovery of Hawking radiation in 1974 was a moment of profound and revolutionary insight, a theoretical breakthrough that forever changed our understanding of black holes and forged a deep and unexpected link between the disparate worlds of general relativity, quantum mechanics, and thermodynamics. Until that point, black holes were seen as the ultimate cosmic prisons, perfect absorbers that swallowed everything, including light, and from which nothing could ever escape. They were thought to be completely black, completely cold, and, in a sense, completely dead. Hawking's brilliant and subtle calculation turned this picture on its head. He showed that when the principles of quantum field theory are applied in the curved spacetime around a black hole, something remarkable happens. The quantum vacuum, which we now understand to be a seething sea of virtual particle-antiparticle pairs, is disturbed by the intense gravity near the event horizon. This can lead to a process where one member of a virtual pair falls into the black hole, while the other escapes to infinity. To an outside observer, it appears as if the black hole is emitting a steady stream of particles. The particle that fell in must have a negative energy to conserve the total energy of the system, which means that the black hole loses a tiny amount of its mass energy with each emitted particle. The black hole is not black, it radiates. And this radiation, the Hawking radiation, has a perfect thermal blackbody spectrum with a temperature that is inversely proportional to the black hole's mass. This means that smaller black holes are hotter and radiate more intensely than larger ones. For a macroscopic, stellar mass black hole, this temperature is incredibly, almost unmeasurably, low, a tiny fraction of a degree above absolute zero. But for a microscopic, primordial black hole, the temperature could be immense. This process of radiation means that black holes are not eternal. They evaporate. As a black hole radiates, it loses mass, which causes its temperature to increase, which in turn causes it to radiate even faster. This creates a runaway process that accelerates over time, culminating in a final, explosive burst of high-energy radiation as the black hole disappears completely. This discovery had a profound impact on the field of physics, as it provided the first concrete example of a physical process that requires a combination of all three of the great theories of the 20th century. It is a phenomenon that is fundamentally gravitational, fundamentally quantum, and fundamentally thermodynamic. This led to the development of the field of black hole thermodynamics, a beautiful and consistent mathematical framework that shows a deep and surprising analogy between the laws of black hole mechanics and the laws of classical thermodynamics. The first law of black hole mechanics, which relates changes in a black hole's mass to changes in its area, spin, and charge, is the direct analog of the first law of thermodynamics, the conservation of energy. The second law of black hole mechanics, Hawking's area theorem, which states that the surface area of a black hole's event horizon can never decrease in a classical process, is the analog of the second law of thermodynamics, the law of increasing entropy. In fact, the physicist Jacob Bekenstein had proposed, even before Hawking's discovery, that the area of a black hole's event horizon is a measure of its entropy, its hidden information content. Hawking's discovery of thermal radiation provided the missing piece of the puzzle, the temperature, which allowed for a complete and consistent thermodynamic description. The third law of thermodynamics, which states that it is impossible to reach absolute zero temperature, has its black hole analog in the statement that it is impossible to create a black hole with a zero surface gravity, an extremal black hole. The discovery of Hawking radiation was a moment of stunning unification, a glimpse of the deep and beautiful connections that lie at the heart of our physical theories. But it also, as we have seen, opened up a Pandora's box of new and profound puzzles, most notably the information paradox, a puzzle that has driven much of the progress in theoretical physics for the past 50 years, and one that continues to challenge and inspire us in our quest for a final, unified theory of everything. The black hole information paradox, born from the clash between Hawking's discovery of thermal radiation and the fundamental principles of quantum mechanics, is one of the deepest and most consequential puzzles in all of theoretical physics. It is a paradox that has forced us to question our most basic assumptions about the nature of information, of space-time, and of reality itself. The core of the paradox is a stark contradiction. Quantum mechanics, at its very foundation, is built on the principle of unitarity, the idea that information is never truly lost. The wave function of a closed system evolves in a perfectly deterministic and reversible way. If you know the state of the system at one time, you can, in principle, calculate its state at any other time, either in the future or in the past. Information is scrambled, not destroyed. General relativity, on the other hand, seems to tell a different story. The event horizon of a black hole is a one-way membrane. Information can fall in, but it can never get out. And when the black hole completely evaporates into a seemingly random thermal bath of Hawking radiation, the information about the matter that formed it appears to be gone forever, erased from the universe in a way that fundamentally violates the principle of unitarity. This is the paradox. For decades, this was a battle between the two giants of 20th century physics. On one side, you had the quantum purists, who insisted that unitarity must be preserved at all costs, even if it meant that our understanding of space-time and causality had to be radically altered. On the other side, you had the relativists, including, for a long time, Stephen Hawking himself, who argued that the information was truly and irretrievably lost, and that quantum mechanics would have to be modified to accommodate this new gravity-induced non-unitarity. The debate has been long, technical, and often acrimonious. But over the years, the consensus has slowly shifted in favor of information preservation. The theoretical evidence from string theory and the ADS-CFT correspondence has provided powerful, if indirect, arguments that the process of black hole evaporation must be unitary. This has led to a host of creative and often bizarre proposed solutions to the paradox. One of the earliest ideas was that of black hole remnants. Perhaps the black hole does not evaporate completely. Perhaps it leaves behind a tiny, stable, Planck mass relic that contains all the information that fell in. This would preserve unitarity. But it comes with its own set of problems. An infinite amount of information would have to be stored in a tiny, finite object, and the universe would be filled with these otherwise undetectable relics, which would have profound cosmological consequences. Another, more mainstream, idea is that the information is not lost, but is subtly encoded in the outgoing Hawking radiation. The radiation is not perfectly thermal, but contains tiny, almost imperceptible quantum correlations that carry the information about the black hole's history. This is the most conservative and, for many, the most plausible solution. The problem is that it is incredibly difficult to show how this information encoding would work in detail. It seems to require a form of spooky, non-local interaction at the event horizon, a violation of the classical, local picture of space-time. This has led to some of the most radical and controversial ideas in modern physics. The concept of black hole complementarity, proposed by Leonard Susskind and others, suggests that the information is both inside the black hole and outside, encoded in the radiation, but that no single observer can ever see both at the same time, thus avoiding a logical contradiction. More recently, the firewall paradox, posed by a group of physicists in 2012, has argued that the assumptions of complementarity are inconsistent, and that an observer falling into an old black hole would be incinerated by a firewall of high-energy particles at the event horizon. This would preserve unitarity, but at the cost of violating one of the most cherished principles of general relativity, the equivalence principle, which states that the laws of physics should be the same for all observers, including one in free fall. The information paradox is still far from being resolved. It is a deep and complex problem that touches on the very foundations of our understanding of the universe, but it is also a powerful and productive one. It has been a crucible for new ideas, a testing ground for our theories of quantum gravity, and a constant reminder that the universe, at its most fundamental level, is far stranger, more subtle, and more beautifully interconnected than our classical intuition can ever hope to comprehend. The answer, when it finally comes, will likely involve a radical rethinking of our concepts of space-time, of locality, and of information itself. The strange and wonderful phenomenon of quantum entanglement, the spooky action at a distance that so vexed Einstein, has, in recent years, emerged as a central and surprisingly powerful player in the ongoing drama of the black hole information paradox. It is an idea that suggests that the deep, non-local connections of the quantum world may be the key to understanding the deep, gravitational mysteries of black holes. The connection is a natural one. The process of Hawking radiation itself is fundamentally an entanglement phenomenon. The virtual particle-antiparticle pair created at the event horizon is an entangled system. When one particle falls in and the other escapes, the escaping particle remains entangled with its partner inside the black hole. As the black hole continues to radiate, it becomes more and more entangled with the radiation that it has emitted. This is the source of the information paradox. The principle of monogamy of entanglement in quantum mechanics states that a quantum system can only be maximally entangled with one other system at a time. The outgoing Hawking radiation particle is already maximally entangled with its partner inside the black hole. But for the information to get out, it must also become entangled with the radiation that was emitted earlier. This is a quantum impossibility, a logical contradiction that lies at the heart of the firewall paradox. This has led to a revolutionary and beautiful idea, the ER-EPR conjecture. This conjecture, proposed by physicists Juan Maldacena and Leonard Susskind, suggests a deep and unexpected equivalence between two of Einstein's most famous and seemingly unrelated ideas. EPR refers to the Einstein-Podolsky-Rosen paradox, the thought experiment that first highlighted the strange, non-local nature of quantum entanglement. ER refers to the Einstein-Rosen bridge, the original name for what we now call a wormhole, a theoretical tunnel through spacetime that could connect two distant points. The ER-EPR conjecture proposes that these two concepts are, in fact, two different descriptions of the same, underlying physical reality. A pair of entangled particles is, in a deep, geometrical sense, connected by a wormhole. The spooky, non-local correlation of entanglement is the quantum manifestation of this hidden geometrical connection. This is a staggering idea, one that weaves together the fundamental principles of quantum mechanics and general relativity in a new and profound way. It suggests that the very fabric of spacetime may be emergent from the web of quantum entanglement, and it has profound implications for the information paradox. In the ER-EPR picture, the inside of the black hole is not a separate, causally disconnected region. It is geometrically connected to the outgoing Hawking radiation via a vast and complex network of microscopic wormholes. The information is not trapped inside, it is non-locally present in the radiation outside. Through these entangled wormhole connections, the interior of the black hole is, in a sense, built from the same quantum degrees of freedom that make up the radiation. This is a concept that is deeply tied to the holographic principle. It provides a specific, dynamical mechanism for how the information in the three-dimensional bulk of the black hole can be encoded in the two-dimensional boundary of the outgoing radiation. It is a picture that is still being developed, and it is full of technical and conceptual challenges. But it is one of the most exciting and promising ideas in modern theoretical physics. It suggests that the solution to the information paradox will not be found in a small modification to our existing theories, but in a complete and radical rethinking of the relationship between quantum mechanics and the geometry of spacetime. It is a vision where the strange, non-local connections of the quantum world are not just a bizarre feature of reality, but are the very threads from which the fabric of spacetime itself is woven. Entanglement is not just a spooky action at a distance, it may be the very glue that holds the cosmos together. The cosmic stage is not just set by the familiar actors of matter and energy that we can see and touch. The vast majority of the universe's inventory, about 95% of its total mass energy content, is made up of two mysterious and invisible entities, dark matter and dark energy. And in a surprising and controversial new development, some scientists have proposed a deep and unexpected connection between these two great cosmic mysteries. A connection that is mediated by the universe's most enigmatic objects, black holes. Dark matter is the invisible scaffolding of the cosmos. It is a mysterious, non-luminous substance that does not interact with light, but whose gravitational influence we can see everywhere. It is what holds galaxies together, preventing them from flying apart. It is what shapes the large-scale structure of the universe, the vast cosmic web of filaments and voids. We know it is there, but we do not know what it is. It is likely a new, undiscovered type of fundamental particle, one that interacts only weakly with the particles of the Standard Model. Dark energy, as we have seen, is the even more mysterious force that is driving the accelerating expansion of the universe. It is a smooth, uniform energy that seems to be an intrinsic property of space itself, a form of cosmic anti-gravity. For a long time, these two dark components of the universe were thought to be completely separate and unrelated phenomena, but a recent and provocative theory has proposed a startling connection. The theory, developed by a team of astrophysicists, including Duncan Farah, suggests that black holes themselves could be the source of dark energy. This idea has its roots in a concept from the 1960s, which proposed that a hypothetical object made of pure vacuum energy would, from the outside, look and behave gravitationally just like a black hole. But instead of having a singularity at its center, it would be a smooth, non-singular object, its repulsive vacuum energy balanced by its own gravitational pull. The new theory takes this idea a step further. It proposes that black holes are not just made of collapsed matter, but are coupled to the expansion of the universe itself. They contain a core of vacuum energy, and as the universe expands, this vacuum energy core also grows, causing the mass of the black hole to increase over time. This is a radical idea. It means that the mass of a black hole is not just determined by what it eats, but also by the evolution of the cosmos as a whole. This is a testable prediction. If black holes are growing in this way, then the supermassive black holes at the centers of galaxies should be more massive relative to their host galaxies in the present-day universe than they were in the early universe. And this is exactly what the proponents of the theory claim to have found. By comparing the masses of supermassive black holes in distant, dormant, elliptical galaxies with those in nearby, similar galaxies, they found that the nearby black holes are significantly more massive by a factor of 7 to 20 than their distant counterparts. This suggests that the black holes have been growing over cosmic time, not by eating, but by cosmological coupling. This is a highly controversial result, and it is still being debated in the astronomical community. Many other astrophysicists argue that this apparent growth can be explained by other, more conventional, astrophysical processes, such as the selection bias in the samples of galaxies being studied, or the complex and not fully understood history of galactic mergers. But if the result holds up to further scrutiny, its implications would be profound. It would mean that dark energy is not a smooth, uniformly distributed field, but is localized within the hearts of black holes. It would provide a direct, physical source for the cosmic acceleration, and it would forge a deep and unexpected link between the two greatest mysteries of modern cosmology. It is an idea that is still in its infancy, and it faces many theoretical and observational challenges. For example, the total mass of all the black holes in the universe is still far too small to account for the observed amount of dark energy. But it is a beautiful and creative idea, one that is forcing us to rethink our most basic assumptions about the nature of black holes, of dark energy, and of the intricate and beautiful connections that bind our universe together. The study of black holes, in all their varied and wonderful forms, is one of the most vibrant and exciting frontiers in modern science. It is a field where the deepest questions of fundamental physics meet the most advanced observational technologies. A place where we can probe the very limits of our understanding of gravity, of space-time, and of the quantum universe. From the classical, macroscopic black holes born from the death of massive stars to the hypothetical, microscopic quantum black holes that could be created in our particle accelerators. These enigmatic objects are a rich and fertile ground for discovery. The classical view of a black hole as a simple, featureless object, described only by its mass, charge, and spin, has given way to a much more nuanced and complex quantum picture. We now understand that black holes have a temperature, an entropy, and that they radiate and evaporate over immense timescales. This has led to the profound information paradox, a puzzle that has been a driving force in theoretical physics for half a century and has led to some of our deepest insights into the nature of quantum gravity, including the holographic principle and the ERR-EPR conjecture. The study of the different flavors of black holes, the spinning Kerr black holes with their frame-dragging ergospheres, the charged Reissner-Nordstrom black holes with their complex multi-horizon structure, the exotic, higher-dimensional black strings and black brains of string theory is constantly pushing the boundaries of our theoretical understanding and providing new windows into the mathematical structure of the universe. And the development of black hole analogs in the laboratory, systems that mimic the properties of event horizons in controlled, condensed matter settings, is allowing us to test some of the most fundamental predictions of black hole physics, like Hawking radiation, in an experimental setting for the very first time. The recent and highly speculative proposal that black holes could be the source of dark energy is a testament to the enduring power of these objects to inspire new and creative thinking. It is an idea that, while still unproven, has the potential to unify two of the greatest mysteries in cosmology and to fundamentally change our picture of the universe's evolution. The future of black hole research is bright. With a new generation of gravitational wave detectors, like LISA, we will be able to hear the mergers of supermassive black holes across the cosmos, providing an unprecedented probe of the dynamics of spacetime in the strong field regime. With powerful new telescopes, like the James Webb Space Telescope and the Event Horizon Telescope, we will be able to see the environment around black holes with ever-increasing resolution, testing the predictions of general relativity and searching for the subtle signatures of new physics. And with more powerful particle accelerators, we may one day even create a microscopic black hole in the laboratory, opening up a direct experimental window into the world of quantum gravity and extra dimensions. Black holes are no longer just the stuff of science fiction. They are real, physical objects, and they are one of the most powerful tools we have in our ongoing quest to understand the deepest secrets of the universe. They are the ultimate cosmic laboratory, a place where the familiar laws of our world are pushed to their breaking point, and where the new, more profound, and more beautiful laws of a final, unified theory may be waiting to be discovered. Galaxies, those magnificent islands of stars, dust, and dark matter, have held a profound and enduring grip on the human imagination for centuries. From the faint, milky smudge of our own galaxy arching across a dark night sky to the stunning, detailed portraits of distant spirals captured by our most powerful telescopes. They are the grand architectural pillars of the cosmos. At first glance, they might seem like isolated, self-contained entities, marbles of light scattered across the vast, dark expanse of space. We see the elegant, pinwheeling arms of spiral galaxies, the serene, golden glow of elliptical giants, and the chaotic, misshapen forms of irregulars, hinting at a history of violent, cosmic collisions. But this picture of isolation is a profound illusion. These galactic structures are not solitary islands. They are the luminous nodes in a vast interconnected tapestry that weaves the entire universe together. This is the cosmic web, an immense and intricate network of filaments stretching for billions of light years across the cosmos, a celestial superhighway of matter and energy. At the intersections of these filaments, we find the great galaxy clusters, the bustling metropolises of the universe. The filaments themselves are the cosmic byways, trails of galaxies and intergalactic gas that connect these clusters, while the vast, seemingly empty voids in between are the silent, dark countrysides. The very existence of this cosmic web raises a host of deep and fundamental questions. Why do galaxies cluster along these specific, filamentary structures? What invisible forces guide the flow of matter across the immense voids? The answers, we are learning, lie beyond the realm of the visible. They lead us into the domain of the unseen, the mysterious, and the profoundly powerful. The grand architectural scaffolding of the cosmic web is not built from the stars and gas we can see. It is shaped by a mysterious and invisible substance known as dark matter. This enigmatic entity, which we cannot see or touch, which does not emit, absorb, or reflect any form of light, is the silent, gravitational majority of the universe, outweighing all the normal, baryonic matter by a factor of more than 5 to 1. It is the unseen hand that has guided the formation of every galaxy, every cluster, every filament in the cosmos. But dark matter is not the only invisible force at play. Looming at the heart of almost every massive galaxy is a supermassive black hole, a region of space-time where gravity is so intense that nothing, not even light, can escape. These are not passive, cosmic drains, silently swallowing matter. They are dynamic and powerful engines, their immense gravitational pull dictating the orbits of billions of stars, and their ferocious, high-energy outbursts of radiation and particles regulating the very process of star formation within their host galaxies. They are a profound paradox, a point of ultimate destruction that is also a key agent of cosmic order and creation. And the cosmic drama does not end with these internal forces. Galaxies are social creatures. They are constantly interacting, their immense gravitational fields reaching out across millions of light years to pull on their neighbors. These interactions can be subtle, a gentle tidal stripping of a small satellite galaxy by its massive host, or they can be cataclysmic, a head-on collision between two spiral galaxies of equal size. These major mergers are some of the most spectacular and transformative events in the universe. Cosmic dances of creation and destruction that unfold over hundreds of millions of years. As the two galaxies collide, their vast clouds of interstellar gas are compressed, triggering a furious burst of star formation. A starburst that can briefly outshine all the other stars in the galaxy combined. The elegant spiral structures are torn apart, their stars flung into long tidal tails, and eventually the two galaxies will merge into a single, larger, and often elliptical galaxy. These collisions are a primary driver of galactic evolution, shaping the size, the structure, and the destiny of the galaxies we see today. But even as we begin to understand this intricate dance of dark matter, black holes, and galactic collisions, we are confronted with an even deeper and more pervasive mystery, the existence of dark energy. This is a strange, repulsive force, a property of space itself, that is causing the expansion of the entire universe to accelerate. While its existence is now well established by our observations, its fundamental nature remains a complete enigma. Is it a constant, unchanging property of the vacuum, or is it a dynamic entity whose strength changes over cosmic time? The answer to this question will determine the ultimate fate of our universe, and the ultimate fate of the very galaxies we are trying to understand. And then there is the most profound question of all, the question that underlies all of our cosmological inquiries. Why does the universe exist in this particular form? Could it have been different? Are there other parallel realities? Other universes where the laws of physics are different, where galaxies formed in a completely different way? Or perhaps where they never formed at all? These are the grand, open-ended puzzles that fuel the relentless, passionate curiosity of astronomers, physicists, and cosmologists. Every star, every orbit, every galactic spin is a thread in the cosmic tapestry, a clue in a detective story that is billions of years in the making. Today, we begin to pull on some of these threads, to peel back the cosmic veil, and to explore the forces, the entities, and the enigmas that have shaped the magnificent galactic islands we call home. The story of galaxy formation begins not with stars or gas, but in the fiery primordial crucible of the Big Bang itself. This is the moment, some 13.8 billion years ago, when not just matter and energy, but space and time themselves exploded into being. The popular image of the Big Bang as an explosion in space is a misleading one. It was an expansion of space, an event that happened everywhere at once, in the first infinitesimal fractions of a second. The universe was an unimaginably hot and dense singularity, a point of infinite temperature and density where our current laws of physics break down. This was followed by a period of astonishing, hyper-accelerated expansion known as cosmic inflation, a process that stretched the nascent universe from a subatomic size to something larger than a grapefruit in a time far shorter than the blink of an eye. As this inflationary period ended, its immense energy was converted into a hot, dense soup of fundamental particles. This was the true beginning of the hot Big Bang phase. At these extreme temperatures, well into the trillions of degrees, the familiar particles of our world could not exist. The universe was a quark-gluon plasma, a chaotic, seething sea of the most fundamental building blocks of matter quarks and the gluons that bind them along with photons, electrons, and other elementary particles. As the universe continued to expand and cool, it passed through a series of critical phase transitions. After about 1 microsecond, the temperature had dropped enough for the quarks and gluons to freeze out, combining in groups of 3 to form the first protons and neutrons, the building blocks of atomic nuclei. This was a pivotal moment, but it was also a moment of profound and enduring mystery. The laws of physics, as we understand them, are almost perfectly symmetric with respect to matter and antimatter. For every type of particle, there should be an antiparticle with the same mass but opposite charge. In the intense heat of the early universe, particles and antiparticles should have been created in equal amounts. And when a particle meets its antiparticle, they annihilate each other in a burst of pure energy. This means that as the universe cooled, almost all the matter and antimatter should have annihilated, leaving behind a universe filled with nothing but a diffuse bath of radiation. But this is not what we see. We live in a universe that is made almost entirely of matter. For every billion antiparticles in the early universe, there must have been 1,000,000,001 particles of matter. This tiny 1 in a billion imbalance. This slight preference of the universe for matter over antimatter is the reason that we exist. The process that created this imbalance is known as baryogenesis, and its precise mechanism remains one of the great unsolved puzzles in modern physics. It is a mystery that is deeply connected to the fundamental symmetries of nature, and its solution will likely require a new physics beyond our current standard model. As the universe continued its journey of cooling and expansion, it entered the next crucial phase of its early evolution, Big Bang nucleosynthesis. Between about 1 and 3 minutes after the Big Bang, the temperature had dropped to a mere billion degrees, cool enough for the protons and neutrons to begin to fuse together. Forming the nuclei of the first light elements, the universe became a primordial nuclear reactor. Protons and neutrons combined to form deuterium, which then fused to form helium-4, along with trace amounts of helium-3, lithium, and beryllium. This process was incredibly efficient, but also very short-lived. After about 20 minutes, the universe had expanded and cooled to the point where nuclear fusion was no longer possible. The result was a universe whose baryonic matter was composed of about 75% hydrogen nuclei, 25% helium nuclei, and a tiny fraction of lithium. The precise predictions of Big Bang nucleosynthesis for the abundances of these light elements are one of the great triumphs of the Big Bang model, matching our observational measurements with stunning accuracy. But for the next 380,000 years, the universe remained a hot, dense, and opaque plasma. The temperature was still too high for the newly formed atomic nuclei to capture the free-roaming electrons. This sea of free electrons acted like a dense fog, constantly scattering the photons of light and preventing them from traveling any significant distance. The universe was a glowing but impenetrable haze. Then, as the universe reached the age of 380,000 years, it crossed another critical threshold. The temperature dropped to about 3,000 Kelvin, cool enough for the electrons to finally be captured by the atomic nuclei, forming the first stable, neutral atoms. This event is known as recombination or decoupling. Suddenly, the cosmic fog lifted. The universe became transparent to light. The photons that had been trapped in the primordial plasma were now free to travel unimpeded through the expanding space, and they have been traveling ever since. Their wavelength stretched by the subsequent expansion of the universe from the high-energy light of a glowing fireball into the cool, faint microwaves that we detect today from all directions in the sky. This is the cosmic microwave background, the oldest light in the universe, a beautiful and incredibly informative fossil of the infant cosmos. The CMB is not perfectly uniform. It contains tiny, almost imperceptible temperature fluctuations, variations of about 1 part in 100,000. These tiny anisotropies are the imprints of the initial density fluctuations in the primordial universe, the quantum ripples from the inflationary epoch that were stretched to astronomical scales. These fluctuations are the seeds of all cosmic structure. The slightly denser regions were the gravitational wells into which matter would later fall, the birthplaces of the first stars and galaxies. The slightly less dense regions would become the great cosmic voids. The CMB is a baby picture of our universe, a snapshot of the moment it first became transparent, a map of the primordial seeds from which the entire, glorious and complex tapestry of the cosmos would eventually grow. The period following the release of the cosmic microwave background, from about 400,000 years to a few hundred million years after the Big Bang, is known as the Cosmic Dark Ages. The universe was now transparent, but it was also dark. The primordial fireball had faded, and there were not yet any stars or galaxies to light up the cosmos. The universe was a vast, expanding, and slowly cooling expanse of neutral hydrogen and helium gas, with the tiny primordial density fluctuations sown by inflation gently growing under the influence of gravity. The Dark Ages were a time of quiet gestation, a period where the seeds of cosmic structure were slowly, patiently beginning to sprout. In the slightly denser regions of the universe, gravity began to win its long battle against the outward pressure of the gas. The neutral hydrogen and helium began to clump together, forming vast, filamentary structures, the first skeletal outlines of the cosmic web. The dominant gravitational player in this process was not the normal, baryonic matter, but the mysterious, invisible dark matter. Because dark matter does not interact with light, it was not coupled to the radiation pressure of the early universe. It was free to begin clumping and forming gravitational halos long before the baryonic matter. These dark matter halos acted as the gravitational seeds, the cosmic nurseries into which the normal gas would later fall. Over millions of years, the gas within these dark matter halos became denser and denser. As it was compressed, it began to heat up. But for a star to form, the gas must be able to cool, to radiate away its heat, so that gravity can continue its work of compression. The primordial gas of the Dark Ages, composed almost entirely of hydrogen and helium, was a very inefficient coolant. It took a long time and a lot of mass for a gas cloud to cool enough to trigger the first star formation. But eventually, in the densest hearts of the most massive of these early dark matter halos, the conditions became right. The first stars were born. The ignition of these first stars, known as population 3 stars, marks the end of the cosmic dark ages and the beginning of the cosmic dawn. These were not like the stars we see today because they formed from the pristine, metal-free gas of the early universe. They were incredibly massive, perhaps hundreds of times the mass of our sun. And because of their immense mass, they were incredibly hot, incredibly luminous, and incredibly short-lived. They blazed with a fierce, blue-white light, flooding the surrounding darkness with the first starlight the universe had ever known. Their intense, high-energy ultraviolet radiation began to ionize the neutral hydrogen gas around them, creating expanding bubbles of ionized plasma in the surrounding dark. And their lives ended in spectacular, cataclysmic supernova explosions that seeded the universe with the first heavy elements, the metals that would be essential for the formation of the next generation of stars, of planets, and of life itself. These first stars were the pioneers, the cosmic trailblazers who lit up the darkness and began the long, complex process of transforming the simple, primordial universe into the rich, chemically diverse, and life-bearing cosmos we inhabit today. The birth of the first stars triggered a cascade of structure formation in the early universe. The dark matter halos that hosted these stars continued to grow, merging with their neighbors to form larger and larger structures. Within these halos, the gas, now enriched with the first heavy elements from the population 3 supernovae, could cool more efficiently, leading to the formation of the first protogalaxies. These were small, irregular, and chaotic systems, a far cry from the grand, ordered spiral galaxies we see today. They were the building blocks, the cosmic Legos, from which the larger galaxies would be assembled over billions of years. This is the hierarchical or bottom-up model of galaxy formation, the current standard paradigm in cosmology. In this picture, small things form first, and then merge to form bigger things. The early universe was a violent and dynamic place, a cosmic construction site where these proto-galaxies were constantly colliding and merging, triggering intense bursts of star formation. The James Webb Space Telescope has given us our first tantalizing glimpses into this chaotic early epoch. It has observed galaxies that were already in place just a few 100 million years after the Big Bang. Their light red-shifted into the infrared by the expansion of the universe. And these early galaxies are not always the small, messy objects our models predicted. Some of them appear to be surprisingly large, surprisingly massive, and surprisingly well-organized, challenging our understanding of how quickly these structures could have formed. As these first proto-galaxies grew and evolved, their combined radiation, along with the radiation from the first quasars, began to have a profound impact on the universe as a whole. This was the epoch of reionization. The bubbles of ionized hydrogen created by the first stars and galaxies began to grow and overlap, until, by about 1 billion years after the Big Bang, the entire vast expanse of the intergalactic medium had been transformed from a cold, neutral gas back into a hot, ionized plasma. The universe, which had been dark and opaque during the Dark Ages, was now transparent and filled with light once again. This was a fundamental phase transition for the cosmos, a second coming of age that set the stage for the evolution of the large-scale structures we see today. The epoch of reionization was not a simple, uniform process. It was a patchy, complex affair, with some regions of the universe becoming ionized earlier than others, depending on the local density of stars and galaxies. Mapping this process in detail is one of the primary goals of modern cosmology, as it holds the key to understanding the nature of the first luminous sources and their impact on the cosmic environment. Observatories like the Square Kilometre Array are designed to detect the faint 21-centimeter radio signal from the neutral hydrogen of the Dark Ages and the epoch of reionization, which will allow us to create a three-dimensional map of this crucial transformative period in our universe's history. The story of the first stars and galaxies is a story of how, from the quiet darkness of a simple primordial state, the first points of light emerged, and how that light, in turn, transformed the entire cosmos, setting the stage for the rich, complex, and beautiful universe we now inhabit. It is a story of how the universe lit its own fire, a fire that continues to burn in the hearts of billions of galaxies, including our own. The galaxies we see in the universe today are not a random assortment of shapes and sizes. They fall into a surprisingly well-ordered classification scheme, a tuning fork diagram first developed by the great astronomer Edwin Hubble in 1926. This scheme, which is still the starting point for our understanding of galaxy morphology, divides galaxies into three main classes: ellipticals, spirals, and irregulars. Elliptical galaxies are smooth, featureless, and often spheroidal or football-shaped collections of stars. They are the old red and dead galaxies of the universe. They are dominated by old reddish stars. They contain very little cold gas and dust, and they have very low rates of ongoing star formation. They are the calm, stately, and retired citizens of the cosmic city. Spiral galaxies, like our own Milky Way, are the vibrant, active, and youthful members of the galactic population. They are characterized by a flat, rotating disk of stars, gas, and dust, with beautiful, elegant spiral arms where new, hot blue stars are constantly being born. They often have a central, spheroidal bulge of older stars, and many, including our own galaxy, have a central bar-like structure from which the spiral arms emerge. These are the barred spiral galaxies. Irregular galaxies, as their name suggests, are the misfits, the rebels of the cosmic zoo. They lack any clear, defined structure. They are often chaotic, clumpy, and rich in gas and dust, with high rates of vigorous and often bursty star formation. They are the cosmic works in progress, galaxies that are still in the process of being assembled or have recently been disturbed by a close encounter with a neighbor. The Hubble tuning fork is not just a classification scheme. It is also, in a rough sense, an evolutionary sequence. The current paradigm of galaxy formation, the hierarchical model, suggests that the chaotic, irregular galaxies of the early universe gradually, through a series of mergers and a long period of more quiescent evolution, transform into the grand and ordered spiral and elliptical galaxies we see today. The key driver of this transformation is gravity, which pulls together the dark matter halos, which in turn pull together the gas and the stars. But the story is not just one of gravity. It is a complex interplay of a host of different physical processes, a cosmic dance of feedback and regulation. The process of star formation itself is a powerful feedback mechanism. The intense radiation and powerful stellar winds from young, massive stars can heat and blow away the surrounding gas, inhibiting the formation of further stars. The supernova explosions that mark the end of these massive stars' lives are even more powerful. They inject a huge amount of energy and heavy elements into the interstellar medium, creating vast, expanding superbubbles of hot gas that can clear out entire regions of a galaxy, temporarily shutting down star formation. But this feedback is not just destructive. The shock waves from these supernovae can also compress the surrounding gas clouds, triggering a new wave of star formation. It is a self-regulating cycle of birth, death, and rebirth. On an even larger scale, the supermassive black holes at the centers of galaxies are now known to be crucial players in this cosmic feedback loop. As gas falls towards the central black hole, it forms a hot, luminous accretion disk, which can launch powerful jets and winds that can travel at nearly the speed of light. This active galactic nucleus feedback can be so powerful that it can heat and expel the gas from the entire galaxy, effectively quenching all future star formation. This is thought to be the primary mechanism that transforms large, star-forming spiral galaxies into quiescent, red and dead elliptical galaxies. The beautiful, ordered structures we see in the universe today are not a static, final state. They are the product of a long, violent, and complex history. A history of mergers, of starbursts, of feedback, of a constant, dynamic interplay between the creative force of gravity and the regulatory forces of stellar and AGN feedback. The universe is not just a collection of galaxies, it is a dynamic, evolving ecosystem. And understanding the intricate feedback loops that govern this ecosystem is one of the central goals of modern astrophysics. The evolution of a galaxy is not just determined by its internal processes. It is also profoundly shaped by its environment. A galaxy that lives a solitary life in the middle of a cosmic void will have a very different history from a galaxy that inhabits the dense, crowded heart of a massive galaxy cluster. This is the nature versus nurture debate of cosmology. The nature of a galaxy is its intrinsic properties, like its mass and its angular momentum, which are largely determined by the initial conditions of the dark matter halo in which it formed. The nurture is the influence of its environment, the interactions with its neighbors, and with the larger cosmic web. Both are crucial. An isolated galaxy, a cosmic hermit, can evolve in a relatively peaceful and quiescent way. It can slowly accrete gas from the surrounding intergalactic medium, fueling a steady, long-lived rate of star formation. This is the likely history of many of the beautiful, grand-designed spiral galaxies we see in the field. But a galaxy that lives in a dense cluster is subject to a host of environmental processes that can dramatically alter its fate. As a galaxy falls into a cluster, it moves through the hot, dense intracluster medium, the tenuous gas that fills the space between the cluster galaxies. This can lead to ram pressure stripping, where the galaxy's own interstellar gas is stripped away by its motion through the intracluster medium, like a runner's hair being blown back by the wind. This process can quickly remove a galaxy's fuel for star formation, transforming a blue, star-forming spiral into a red, quiescent S0 or lenticular galaxy. Galaxies in clusters are also subject to more frequent gravitational interactions. Tidal stripping can occur when a smaller galaxy passes close to a larger one, its outer stars and gas being torn away by the stronger gravitational pull of its massive neighbor. We see evidence of this in the long, beautiful tidal streams of stars that are often seen snaking around massive galaxies like our own Milky Way and the Andromeda Galaxy. These streams are the ghostly remnants of dwarf galaxies that have been tidally disrupted and are in the process of being accreted. And of course, there are the direct cataclysmic collisions and mergers. While these are more common in smaller galaxy groups, they can also occur in clusters, leading to the formation of the most massive galaxies in the universe. The giant CD elliptical galaxies that are often found at the very center of rich clusters. These cosmic behemoths are thought to be the product of multiple, repeated mergers over cosmic time. The environment of a galaxy, therefore, plays a pivotal role in its evolution, in a process that is sometimes called galaxy harassment. The dense, violent, and gas-poor environment of a cluster tends to transform star-forming spiral galaxies into quiescent elliptical and S0 galaxies. This is known as the morphology-density relation, a well-observed correlation in the local universe. The cosmic web itself plays a crucial role in this environmental story. The filaments of the web act as the cosmic highways along which galaxies and gas are funneled into the growing clusters at the nodes. Galaxies that live in the filaments are in a transitional environment, still accreting gas and forming stars, but also beginning to feel the gravitational influence of the nearby cluster. They are the suburban galaxies, on their way to the bustling and often brutal life of the cosmic city. Understanding the complex interplay between a galaxy's intrinsic nature and its environmental nurture is one of the key challenges in building a complete picture of galaxy formation and evolution. It requires a combination of large-scale cosmological simulations that can model the growth of the cosmic web and the formation of clusters, and high-resolution zoom-in simulations that can model the detailed, messy physics of star formation, feedback, and galactic interactions within individual galaxies. It is a monumental task, but it is one that is bringing us closer than ever to a complete and beautifully complex understanding of the origin and evolution of the magnificent star islands that we call home. Our own cosmic home, the Milky Way galaxy, and its nearest major neighbor, the Andromeda galaxy, provide us with a unique and powerful laboratory for studying the processes of galaxy formation and evolution up close. They are the two largest members of the local group, a gravitationally bound collection of more than 50 galaxies, and they offer us a detailed archaeological window into the history of a typical large spiral galaxy. The Milky Way is a barred spiral galaxy, a vast rotating disk of about 100 billion stars, with a central bar-like structure and a number of spiral arms. We are located in one of these arms, the Orion Arm, about 27,000 light-years from the galactic center. By meticulously mapping the positions, motions, and chemical compositions of the stars in our galaxy, a field known as galactic archaeology, astronomers are able to piece together the story of its formation. We have learned that the Milky Way, like other large galaxies, was built up over billions of years through the hierarchical merger of smaller protogalactic fragments. The oldest stars in our galaxy are found in its stellar halo, a vast, diffuse, and spherical component that surrounds the disk, and in its central bulge. These stars are typically metal-poor, meaning they have a low abundance of elements heavier than hydrogen and helium, a sign that they formed early in the universe's history, before many generations of stars had had a chance to enrich the interstellar medium. The disk of the galaxy, on the other hand, is home to younger, more metal-rich stars, like our own Sun, and is the site of most of the ongoing star formation. The evidence for the Milky Way's merger history is written in the sky. We see numerous stellar streams, long, coherent trails of stars that are the tidally disrupted remnants of smaller dwarf galaxies that have been, or are currently being, accreted by our own. The Sagittarius Stream, for example, is a vast river of stars that wraps around the entire galaxy, the ghost of a dwarf galaxy that is being torn apart by the Milky Way's immense gravitational pull. These streams are the fossils of our galaxy's cannibalistic past, and by studying their orbits and their stellar populations, we can reconstruct the timeline of our galaxy's assembly. The Andromeda Galaxy, also known as Messier 31, is our cosmic twin, a slightly larger spiral galaxy located about 2.5 million light-years away. It is the most distant object that can be seen with the naked eye, a faint, fuzzy patch in the night sky, and it is on a collision course with our own. In about 4.5 billion years, the Milky Way and Andromeda will begin a long, slow, and spectacular merger, a cosmic dance that will, over hundreds of millions of years, transform the two spiral galaxies into a single, massive elliptical galaxy, which some have nicknamed Milkomeda. This future collision provides us with a real-time preview of one of the most important processes in galaxy evolution. But Andromeda also offers us a unique, external perspective on a galaxy that is very similar to our own, because we see it from the outside. We can study its overall structure, its spiral arms, its stellar halo, in a way that is difficult for our own dust-obscured galaxy. Observations of Andromeda have revealed a history that is remarkably similar to our own, with a vast stellar halo filled with the remnants of past mergers and a complex, clumpy disk that is still actively forming stars. The study of the local group, with its two giant spirals and its retinue of smaller, dwarf satellite galaxies, is a field that is rich with information about the processes of galaxy formation, of feedback, of tidal stripping, of mergers. It is our own local cosmic ecosystem, and by studying it in detail, with telescopes like Gaia, which is mapping the positions and motions of 1 billion stars in our galaxy, and the James Webb Space Telescope, which can peer through the dust to see the individual stars in Andromeda. We are piecing together the story of our own cosmic origins, a story that is both uniquely our own and also a beautiful and representative chapter in the grand universal epic of galaxy formation and evolution. The luminous baryonic matter that makes up the stars and gas of galaxies is only a small fraction of the total cosmic inventory. The vast majority of the matter in the universe, about 85% of it, is in the form of dark matter, a mysterious, invisible substance that does not interact with light. The story of galaxy formation is, in a very real sense, the story of dark matter. It is the dark matter that provides the gravitational scaffolding, the invisible architecture upon which the visible structures of the universe are built. The existence of dark matter was first inferred in the 1930s by the Swiss astronomer Fritz Zwicky, who observed that the galaxies in the Coma cluster were moving far too fast to be held together by the gravity of the visible matter alone. He postulated the existence of some form of Dunkel materia, or dark matter, to provide the extra gravitational glue. His idea was largely ignored for decades, until the 1970s, when the astronomer Vera Rubin made a similar discovery on the scale of individual galaxies. She meticulously measured the rotation curves of spiral galaxies, the speed at which the stars orbit the galactic center as a function of their distance. According to Newtonian gravity, the stars at the outer edges of a galaxy, where the visible matter thins out, should be moving much more slowly than the stars in the inner regions. But Rubin found that the rotation curves were flat. The outer stars were moving just as fast as the inner ones. This was a stunning result, and it provided the most compelling evidence yet for the existence of a vast, extended halo of invisible dark matter surrounding the visible disk of the galaxy. A halo whose gravitational pull was responsible for the high orbital speeds of the outer stars. Since then, the evidence for dark matter has become overwhelming. We see its effects in the gravitational lensing of distant objects by galaxy clusters, in the temperature fluctuations of the cosmic microwave background, and in the very existence of the large-scale structure of the universe. The cosmic web itself is primarily a web of dark matter. The standard model of cosmology is now the lambda cold dark matter model, where cold dark matter is the specific type of dark matter that is thought to make up the bulk of the universe's mass. Cold in this context means that the dark matter particles were moving slowly in the early universe, which allows them to clump together easily and form the small-scale structures, the dark matter halos, that are the seeds of galaxy formation. The story of galaxy formation, then, begins with the dark matter. In the early universe, the tiny quantum fluctuations from inflation created small overdensities in the otherwise uniform distribution of dark matter. These overdensities began to grow under the influence of their own gravity, collapsing to form the first small dark matter halos. This is a hierarchical, bottom-up process. Small halos form first, and then, over cosmic time, they merge to form larger and larger halos. The normal baryonic matter is, at first, just a passive bystander in this process. But after the universe becomes transparent at the time of recombination, the baryonic gas is free to fall into the deep gravitational potential wells of these pre-existing dark matter halos. It is within these dark matter cocoons that the gas can cool, condense, and form the first stars and galaxies. The properties of a galaxy, its mass, its size, its shape, are thought to be largely determined by the properties of the dark matter halo in which it resides. The distribution of dark matter is not just a passive scaffolding. It is the genetic code that dictates the form and evolution of the visible galaxy. While the LCDM model has been remarkably successful in explaining the large-scale structure of the universe, it does face some challenges on smaller, galactic scales. The cusp core problem. The fact that the centers of some dark matter halos appear to be less dense than the cuspy profiles predicted by simple CDM simulations. And the missing satellites problem. The fact that we observe fewer small dwarf satellite galaxies around the Milky Way than the simulations predict have led some to question the simple, collisionless nature of cold dark matter. These small-scale crises may be solved by a more sophisticated understanding of the messy baryonic physics of feedback, which can heat and expel matter from the centers of galaxies. Or they may be a hint that the nature of dark matter is more complex than we think. Perhaps dark matter is self-interacting, or warm, or has some other exotic property. The quest to identify the dark matter particle is one of the most urgent and exciting challenges in all of modern science. Experiments deep underground are trying to detect the faint, rare interactions of dark matter particles with normal matter. Particle accelerators like the Large Hadron Collider are trying to create dark matter particles in high-energy collisions, and telescopes are searching for the indirect signatures of dark matter annihilation in the gamma-ray sky. The mystery of dark matter is a puzzle that connects the largest structures in the cosmos with the smallest, most fundamental constituents of reality. And solving it will be a crucial step in completing our picture of how the magnificent islands of stars we call galaxies came to be. The story of galaxy formation and evolution is a story of immense complexity, a story that plays out over billions of years and involves a delicate and intricate interplay of gravity, gas dynamics, star formation, stellar feedback, black hole activity, and the mysterious influences of dark matter and dark energy. To understand this complex, multi-scale process, astronomers have turned to one of their most powerful tools, computational simulations. These are not just simple computer models. They are vast, virtual universes, built inside supercomputers, that attempt to replicate the entire 14 billion-year history of the cosmos, from the initial conditions of the Big Bang to the present-day distribution of galaxies. These cosmological hydrodynamic simulations are some of the most complex and computationally expensive calculations ever performed in science. They start with a large, representative volume of the early universe, filled with dark matter and baryonic gas, and with the tiny primordial density fluctuations predicted by the theory of inflation. The simulation then evolves this virtual universe forward in time, step by step, calculating the gravitational forces between all the particles, the complex hydrodynamics of the gas as it cools, collapses, and shocks, and the subgrid physics of star formation and feedback, which are too small scale to be resolved directly, but whose effects are crucial to the overall evolution of the galaxies. The results of these simulations are nothing short of spectacular. They produce virtual universes that look remarkably and often beautifully similar to our own. They show the hierarchical formation of the cosmic web, with dark matter collapsing into filaments and halos. They show the baryonic gas falling into these halos, cooling, and forming rotating disks of stars. They show the violent mergers of galaxies, the triggering of starbursts, the growth of supermassive black holes, and the powerful feedback from supernovae and active galactic nuclei that regulates the growth of the galaxies. Projects like the Illustris and Eagle simulations have been particularly successful in this endeavor. These simulations have been able to reproduce, with remarkable accuracy, a host of observed properties of the galaxy population, such as the galaxy mass function, the morphology-density relation, and the bimodal color-magnitude diagram. These successes have given us a great deal of confidence in the overall hierarchical LCDM paradigm of galaxy formation. They have shown us that our basic picture of how the universe is put together is, in all likelihood, correct, but these simulations are not just about confirming what we already know. They are also powerful tools for discovery. By comparing the detailed predictions of the simulations with the ever more precise observations from telescopes like Hubble and Webb, we can test our understanding of the complex subgrid physics of star formation and feedback. For example, by tweaking the parameters that govern the strength of supernova feedback or AGN feedback in the simulations, we can see what effect this has on the resulting galaxy population. And we can then compare this with the real universe to see which models work best. This is a powerful, iterative process, a dialogue between theory and observation that is constantly refining our understanding of the complex, baryonic processes that shape the galaxies we see. The simulations also allow us to do something that is impossible in the real world: to run the cosmic movie in reverse. To trace the history of a simulated galaxy back in time to understand its unique formation path. We can see which mergers were important, when it had its major bursts of star formation, how its central black hole grew. This provides an invaluable tool for interpreting the snapshots of real galaxies that we see at different cosmic epochs. Despite their immense success, the current generation of cosmological simulations is not without its limitations. They still struggle to accurately model some of the more subtle aspects of galaxy formation, like the structure of the thin disks of spiral galaxies or the abundance of the smallest, faintest satellite galaxies. And they are all, ultimately, based on the assumption that the underlying LCDM model of cosmology is correct. They are powerful tools for understanding the gastrophysics of galaxy formation, but they cannot, by themselves, tell us the nature of dark matter or dark energy. The next frontier for these simulations is to incorporate new physics to explore the consequences of different models of dark matter, of modified gravity, of dynamic dark energy. And as our computational power continues to grow, we will be able to simulate larger volumes of the universe at higher resolution. capturing the complex interplay between the small-scale physics of star formation and the large-scale environment of the cosmic web with ever-increasing fidelity. The virtual universes we build inside our supercomputers are becoming an indispensable tool in our quest to understand the real one. They are a testament to the power of our physical theories and a beautiful and dynamic illustration of the grand to complex and magnificent story of how, from the simple primordial seeds of the early universe, the rich and wonderful tapestry of galaxies we see today was born. The story of galaxy formation is a story written in gas. This is the raw material, the lifeblood of the cosmos, the fuel from which stars are born, and the medium through which the great cosmic cycles of matter and energy play out. Understanding the journey of this gas, from the diffuse primordial soup of the early universe to the dense, star-forming molecular clouds of present-day galaxies, is the key to understanding the entire history of cosmic evolution. In the beginning, the baryonic matter of the universe was a hot, ionized plasma of hydrogen and helium. After recombination, it cooled and became a neutral gas, which then began to fall into the gravitational potential wells of the dark matter halos. As this gas was pulled in, it was shocked and heated to very high temperatures, forming a hot, diffuse corona around the growing protogalaxy. For a star to form, this hot gas must be able to cool and condense. The efficiency of this cooling process is what determines the rate of star formation in a galaxy. In the early universe, the gas was metal-poor, meaning it lacked the heavy elements that are efficient coolants. This made it difficult for the first stars to form. But once the first, population 3 stars exploded as supernovae. They seeded the surrounding gas with the first heavy elements. These metals allowed the gas to cool much more efficiently, triggering a new, more vigorous, and more self-sustaining cycle of star formation. The gas in a modern star-forming galaxy like the Milky Way exists in a complex, multi-phase interstellar medium. There is a hot, ionized medium, heated by supernovae and stellar winds. There is a warm, neutral medium, and there is a cold, dense molecular medium, where the gas is in the form of molecules like molecular hydrogen and carbon monoxide. It is in the coldest, densest hearts of these giant molecular clouds that new stars are born. This interstellar medium is not a static environment. It is a dynamic, turbulent, and constantly evolving ecosystem. Gas is constantly cycling between these different phases, driven by the feedback from star formation. But the gas in a galaxy is not a closed system. Galaxies are constantly accreting fresh, pristine gas from the intergalactic medium, the tenuous gas that fills the space between galaxies. This gas is thought to be delivered to galaxies along the filaments of the cosmic web, in a process known as cold stream accretion. These cosmic rivers of cold gas can penetrate deep into the dark matter halos of galaxies, providing a direct and efficient supply of fuel for ongoing star formation in the disk. This process is thought to be particularly important for fueling the high rates of star formation seen in galaxies in the early universe. At the same time, galaxies are also losing gas. The powerful winds driven by supernovae and active galactic nuclei can be so strong that they can expel gas from the galaxy entirely, launching it into the intergalactic medium in a galactic outflow. This process is crucial for regulating the growth of galaxies and for enriching the IgM with the heavy elements forged in stars. Some of this expelled gas may cool and eventually rain back down onto the galaxy in a galactic fountain, contributing to a cosmic recycling process that can sustain star formation over billions of years. The journey of the gas is a complex and beautiful one, a journey that connects the largest scales of the cosmos with the smallest, the intergalactic with the interstellar, the process of galaxy formation with the birth of individual stars and planets, and it is a journey that we are now able to trace with unprecedented detail. Thanks to a new generation of powerful telescopes, radio telescopes can map the distribution of cold, molecular gas. Optical telescopes can map the distribution of warm, ionized gas, traced by the characteristic red glow of hydrogen alpha emission from star-forming regions. And X-ray telescopes can map the distribution of the hot coronal gas. By combining these different views, we are beginning to build a complete, multi-wavelength picture of the complex, gaseous ecosystem of galaxies, an ecosystem that is the ultimate source of all the structure, all the complexity, and all the life in the universe. The intricate interplay between dark matter and baryonic matter is at the very heart of the story of galaxy formation. Dark matter provides the gravitational scaffolding, the invisible architecture upon which the visible universe is built. But it is the baryonic matter, the gas, the stars, the dust that brings this architecture to life, that creates the light, the color, and the complexity of the galaxies we see. The relationship between these two components is a complex and dynamic one, a cosmic dance that has shaped the evolution of the universe for the past 14 billion years. The dance begins in the early universe. Dark matter, being collisionless, is able to start clumping together early on, forming the first small halos. Baryonic matter, on the other hand, is coupled to the radiation field, and its pressure prevents it from collapsing until after the universe becomes transparent at the time of recombination. After this point, the baryons are free to fall into the pre-existing dark matter halos. But the baryons are not just passive followers. They have their own rich physics. The gas can cool, it can radiate away its energy, and it can collapse to much higher densities than the dark matter. This is why the visible, baryonic part of a galaxy is typically much smaller and more concentrated than its vast, diffuse dark matter halo. The process of star formation and the subsequent feedback from supernovae and active galactic nuclei are purely baryonic processes, but they can have a profound impact on the distribution of the dark matter. The powerful outflows of gas driven by feedback can heat and expand the inner regions of a dark matter halo, potentially softening the central cusp that is predicted by simple, dark matter-only simulations. This baryonic feedback is one of the leading potential solutions to the cusp core problem, one of the small-scale challenges to the standard LCDM model. The relationship between the mass of a galaxy's stars and the mass of its dark matter halo is a crucial diagnostic for our models of galaxy formation. Observations show that this relationship is not a simple, linear one for both very low mass and very high mass halos. The efficiency of converting baryons into stars is very low. In low mass halos, supernova feedback is thought to be so efficient that it can blow most of the gas out of the shallow gravitational potential well, quenching star formation. In very high mass halos, the gas in the corona is so hot that it cannot cool efficiently, and AGN feedback is thought to prevent the gas from accreting onto the central galaxy. It is only in halos with a mass similar to that of our own Milky Way that the star formation efficiency reaches its peak. This Goldilocks effect is a beautiful example of the self-regulating nature of galaxy formation, a process that is governed by the complex feedback loop between the baryonic physics of the galaxy and the gravitational potential of its dark matter halo. But the dance between dark matter and baryons is not just about feedback. It is also about the large-scale environment. In the dense heart of a galaxy cluster, the hot X-ray emitting gas of the intracluster medium can strip the gas from a galaxy, but the dark matter, being collisionless, is unaffected. This can lead to a separation between the baryonic and dark matter components of a galaxy, a process that we can observe directly through a combination of X-ray and gravitational lensing observations. The famous bullet cluster, a system of two colliding galaxy clusters, is the poster child for this effect. The hot gas from the two clusters has collided and shocked, creating a bullet-shaped cloud of X-ray emitting gas, while the dark matter from the two clusters, which we can map through its gravitational lensing effect, has passed right through each other, seemingly unimpeded. This is some of the most direct and compelling evidence we have for the existence of collisionless dark matter. The intricate and often violent dance between the visible and the invisible, between the baryons and the dark matter, is a story that is still being unraveled. It is a story that requires a combination of large-scale cosmological simulations, high-resolution observations across the entire electromagnetic spectrum, and a deep theoretical understanding of the complex physics of the baryonic ISM. But it is a story that is at the very heart of our quest to understand how the universe we see today, with all its beauty and complexity, emerged from the simple, primordial ingredients of the early cosmos. The future of our universe, once a topic reserved for theologians and philosophers, has become a field of active and precise scientific inquiry. The discovery of dark energy and the accelerating expansion of the cosmos has provided us with a new, and in many ways, more definitive, picture of our ultimate cosmic destiny. And it is a picture that is, for the most part, a cold, dark, and lonely one. If dark energy is a true cosmological constant, an unchanging energy of the vacuum itself, as our current observations suggest, then the universe is destined for a big freeze or heat death. The accelerating expansion will continue forever. In the coming billions of years, galaxies beyond our own local group will recede from us at ever-increasing speeds, eventually crossing our cosmic event horizon and disappearing from our view forever. The night sky of the distant future will be a dark and empty place, containing only the aging stars of our own merged Milky galaxy. Over much longer timescales, on the order of trillions of years, the process of star formation will cease. As the gas reservoirs of the galaxies are exhausted, the universe will enter a degenerate era, a time when the only objects left are the cold, dead remnants of stars, white dwarfs, neutron stars, and black holes. Even these objects are not eternal. Over even more immense, almost unimaginable timescales, on the order of 10 to the power of 40 years, protons themselves are predicted to decay, causing the white dwarfs and neutron stars to slowly dissolve into a sea of radiation and leptons. The only objects left will be the black holes, and even they are not forever. Due to Hawking radiation, black holes will slowly evaporate, their mass converted into a faint, thermal radiation. The supermassive black holes at the centers of galaxies will be the last to go, taking perhaps as long as 10 to the power of 100 years to evaporate completely. After this black hole era, the universe will enter its final, eternal state, the dark era. It will be a cold, dark, and almost perfectly empty void. A universe filled with nothing but a diffuse, ever-cooling bath of photons, neutrinos, and a few stray electrons and positrons. It will be a universe in a state of maximum entropy, a state of heat death, where no further thermodynamic work is possible and nothing ever happens again. This is a bleak, but scientifically plausible, vision of the ultimate fate of our cosmos. But what if dark energy is not a constant? If dark energy is a phantom energy whose density increases over time, then the future is far more violent. This leads to the Big Rip scenario. In this case, the accelerating expansion will become so powerful that it will eventually overcome all the other forces of nature. In the final moments of the universe, the repulsive force of the phantom energy will first tear apart galaxy clusters, then galaxies, then solar systems, then planets. And finally, in the last fraction of a second, It will overcome the strong nuclear force and rip apart the atoms themselves, reducing the entire cosmos to a shower of fundamental particles, each forever isolated in an infinitely expanding void. On the other hand, if dark energy is a dynamic quintessence field that could one day decay or change its sign, then the future could be very different. The acceleration could stop, and the universe could even begin to contract, leading to a big crunch, a fiery mirror image of the Big Bang. This opens up the possibility of a big bounce and a cyclic universe, an endless, self-renewing cosmos with no ultimate beginning or end. Distinguishing between these different fates is one of the primary goals of future cosmological observations. By precisely measuring the expansion history of the universe and the properties of dark energy, we can hope to determine whether our cosmos is destined for a slow, cold death, a violent, fiery rip, or an eternal cyclical rebirth. This is a quest that is not just about science. It is about our own, deepest existential questions. It is about understanding the ultimate context of our own brief and precious existence in a universe whose grand cosmic story we are only just beginning to read. The story of the universe, from its fiery birth to its potential cold demise, is a story that has been pieced together through a long and arduous process of scientific inquiry, a process that is a testament to the power and the beauty of the human mind. It is a story that has taken us from the earth-centered cosmos of the ancients to the vast, expanding, and mysterious universe of modern cosmology. And it is a story that is far from over. We are living in a golden age of discovery, a time when a new generation of powerful telescopes and experiments is poised to answer some of the longest-standing questions in science, and to open up new, unforeseen avenues of inquiry. The James Webb Space Telescope is already providing us with our deepest and sharpest views of the infant universe, revealing the first galaxies as they form from the primordial darkness. Future gravitational wave observatories, like the Laser Interferometer Space Antenna, will allow us to hear the universe, to detect the faint space-time ripples from the mergers of supermassive black holes, and perhaps even from the moment of cosmic inflation itself. New large-scale galaxy surveys will map the cosmic web with unprecedented detail, allowing us to trace the history of cosmic expansion and to probe the mysterious nature of dark matter and dark energy. And on the theoretical front, the quest for a unified theory of quantum gravity, a theory of everything, continues. A quest that promises to reveal the deepest secrets of space, time, and the very nature of reality. But for all our progress, for all our powerful theories and our magnificent instruments, we must always remember the profound wisdom of learned ignorance. The more we learn, the more we become aware of the vast, uncharted ocean of our own ignorance. The universe is not a simple puzzle to be solved, but a deep, and perhaps infinite, mystery to be explored, to be wondered at, to be lived. Every answer we find seems to lead to a new, deeper and more beautiful question. The mysteries of the quantum vacuum, of dark energy, of the origin of the arrow of time, of the nature of consciousness itself. These are not just problems for scientists. They are invitations to all of us, to a state of wonder, of curiosity, of humility. They are a reminder that the world is far stranger, far more beautiful, and far more mysterious than our everyday experience would lead us to believe. And as we stand on the shore of this great cosmic ocean, we are not just passive observers. We are the universe's own way of knowing itself. The atoms in our bodies, the consciousness in our minds, are a direct and unbroken lineage from the fiery heart of the Big Bang. We are stardust, animated by the same mysterious life force that has driven the universe's long and magnificent journey from simplicity to complexity. And the quest to understand this universe, this home, is the noblest and most meaningful adventure that we, as a species, can undertake as you close your eyes and prepare for the quiet, restorative journey of sleep. You can feel a sense of participation in this grand, human, and cosmic story, the consciousness that is about to drift into the timeless, mysterious, and creative realm of dreams is the same consciousness that has dared to look up at the stars, to ask the biggest questions, and to begin, however tentatively, to read the silent, beautiful, and endlessly fascinating story of the cosmos. Good night, and may your dreams be as vast, as mysterious, and as wonderful as the universe itself.